Okay, welcome back to Statics 1. What we're going to talk today is about what it means for a system to be in equilibrium and how we draw free body diagrams. And where we're heading with this thing, where we've been really heading ever since the beginning of the course, is that we want to be able to evaluate our support reactions. In other words, what are the reactions of our support? That sounds kind of circular, but imagine we have a beam, and as civil engineers, that's what we usually deal with, are designs of beams, and we have some kind of a loading here, and as we've been talking about, there's going to be supports, and I've commonly drawn it as a hinge at one end and a roller at the other end. And what you're going to find is that you're going to have these characteristic support reactions. So I'll do the support reactions in blue. So the support reactions are essentially saying, you think of it as like the response to loadings. The loadings are like, imagine this is a bridge, these are the cars on the system, these might be some other loads on the system, and the structure that you're building is going to react with forces that are going to hold up the system, hopefully hold up the system isn't going to collapse, and we call these, and I'll leave it in blue here, support reactions. I think I introduced this last time. So that's where we're going. That's what we need to find out as a method, essentially, to evaluate what are these support reactions. In other words, what are the value, the magnitude of those support reactions. So let's present a method of doing this, So we're going to present a method of doing this. And the first thing we need to talk about is what it means if a rigid body, which we've been talking about, remember, rigid bodies are structures or members that do not deform. Okay, so you apply a load, there is always some deformation or some response of bending moments, but we're going to essentially assume them away, which will make the problems much easier to solve. So we're going to talk about the system being in equilibrium. And if a system's in equilibrium, either it's not moving or it's not accelerating. It's moving at a constant velocity. And for our type of problems, we're always dealing with systems that are essentially not moving. So in equilibrium, at least in the general case, it's either not accelerating, or it's not moving. And actually not moving would be a subset of not accelerating. Because if it's not, this would be like moving at a constant velocity. This would be not moving. Obviously not moving. Not moving is moving at a constant velocity of 0. And in fact, we're not really going to deal with this one that much, although mechanical engineers, they do need to deal with it for the most part. But we're talking about essentially bridges, roads, pavement, other things that we're going to build that hopefully are not moving. In some cases, they may be moving like an earthquake or some other kind of wind loads you might have to deal with. But not in Statics 1. We're just dealing with situations where they're not moving. Either of these, if you're in equilibrium, it means you have no unbalanced forces. So all your forces, these are always going to be balanced so that, and I think we've already talked about it, that the sum of the forces, if we're including the support reactions, is going to be equal to 0, where this is a vector. So if we sum up all the forces, it's always going to be equal to 0. And if we sum up all of the moments, that's going to be equal to 0 as well. And that'll be the moments at point 0 plus the force couples, which cause moments as well. This is going to be equal to 0 as well. So that's what it means for a system to be in equilibrium. All right, so when we do this, frequently we're going to be dealing with systems like this, where we're looking at coplanar systems, where all the forces are essentially, they may not be vertically downward, but they're all within the plane, like in the plane of the board, or like in our XY plane. In that case, we might say that this essentially is equivalent to saying that the sum of the forces in the x direction, in other words, if you take the x component of all our forces and add them up, that's going to be equal to 0. The sum of the forces in the y direction equals 0, and the sum of the moments equals 0. So you end up with 3 equations, and a lot of your homework problems, you're going to do this over and over and over again. Get this in your head. Sum of the forces in the x direction, sum of the forces in the y direction, sum of the moments about some point, you can pick the point. They're all going to be equal to 0, and that's how we're going to solve the problem. So you see this, and you have essentially 3 equations, 3 linear equations. If that's the case, if you have 3 linear equations, you can only have 3 unknowns. And that's why we always put a hinge on one end and a roller on the other. So we have 1, 2, 3 unknowns. And we'll talk about next time the different support reactions for hinges, rollers, and other types of supports. Let's see, 3 linear equations. There are, if you ever have, and there's no reason you couldn't have another support. Maybe you put a roller in the middle. Now you have 4 support reactions. 1, 2, 3, 4 support reactions. Unfortunately, in Statics 1, you cannot solve for all 4 of those using this technique. You're going to have to use more advanced techniques that you're going to talk about in Mechanics of Materials or Statics 2 that you're going to deal with next year or next term when you take the class. All right, so that is all I want to talk about now. And in the next talk or next lecture, we're going to talk about the different kind of support reactions and then the drawing of a free body diagram. So that essentially is it. And they'll send me questions if you have any questions, and I'll see you in class.